This is the second part of chapter 2 about process. Here is the subchapter 4, which is about the calculation for process. Before calculating some quantities related to processes, you should understand and recognize what kind of words are very important, and you should understand those words. The first one is basis. Basis is a measure of a process size or scale. The process size is quantified or determined by a quantity, mass or moles, of either a raw material or a desired product in batch processes. Or, in the case of continuous processes, you should use a flow rate like kilogram per second or moles per hour of any process stream. Process can be scaled up or down from an old basis to a new basis. Here is the nitrogen synthesis process. This process has 3 different units: mixer, followed by reactor, followed by separator. Hydrogen, nitrogen are introduced into the mixer, and then they are mixed together. The mixture is introduced into reactor and some reaction there. Finally, you could obtain some ammonia. Unfortunately, we have unreacted amount of hydrogen and nitrogen as the raw materials. So we should separate the desired product ammonia from hydrogen and nitrogen. So you need to have separator. Separator in this case has 2 streams. One is for desired product ammonia, and the other one is for the unreacted hydrogen and nitrogen. Those reactants are going back to the first mixer. This is the process. And at the very first time, when you have designed your process, you have used the basis of 100 kilogram per ton, 100 ton per day. So this process was designed to have 100 ton ammonia per day. This is the basis, and this basis is determining the size of this plant. However, you have changed your mind when you are designing the process. You want to scale up to 1000 ton per day. So this is the old basis, which is 100 ton per day, and right now you have a new basis, 1000 ton per day. The next things you should memorize is system and streams. The system should be defined for calculation something. So system is defined as a specified volume with well-defined boundaries. In this ammonia process, we have 3 units. So the mixer can be taken as the system. This mixer have the very clear boundary, and something is introduced into this boundary, or something is going out of this boundary. So in this first case, the mixer is the system. Or you can extend your system into the reactor. Sometimes you could take those 2 units as a single system, or you could cover all of them, something like that. This case is here, and the whole process was taken as the system, a single system. In this case, we have only one input and only one output. Let me read some text. In a block flow diagram, a single process unit or several process units can be grouped into a single system with boundary. This system has system variables, which is to describe the changes in quantities inside the system. So, some amount of ammonia, hydrogen, nitrogen inside of a system would be system variables. And then let's go to the streams. As you expected, these arrow lines are streams, which are defined as input to and output from a system across its boundary. Also, streams have their own stream variables to describe the quantities or flow rate of materials in a stream. Okay, and also I'd like to define two more things. The first thing is related to stream, and the second one is related to system. Stream composition specification. I'd like to give you some examples. Here, glucose is here, and this glucose is fed to a process. And in this glucose stream, you have a 10% glucose solution in water. So in this case, 10% glucose is the composition. Let's go to the second example. A customer requires that a hydrogen product must be at least 99.9 mole % pure. So you should produce the 99.9 mole % from your separator. So this one, 99.9 mole % is the composition of upstream from your separator. Environmental regulations state that wastewater stream, maybe upstream, must contain no more than 1 gram acetic acid per 1,000 kilogram water. This is a kind of concentration, and also this can be considered as the stream composition specification. Okay, let's go to the second thing. It's about system. System performance specification is the extent of chemical or physical changes inside the system. So this system performance specification characterizes your system. Here are examples. Okay, here is the reactor, and of course this reactor is a kind of the system. And some nitrogen is fed to a reactor and then converted to ammonia. This reactor have a conversion of 65%. That is to say, 65% of the nitrogen feed stream is converted to ammonia. So 65% conversion is characterizing the performance of a reactor, this reactor. Let's go to the second example. There is a splitter, and some fruit juice stream is fed to this splitter, and then the splitter have two different upstream. The first stream have 2/3 of the fruit juice, and the second stream have 1/3 of the fruit juice. So I can say your splitter have some performance to split into two streams, and also one of the upstream have 2/3 of fruit juice. So 2/3 or 67% is the performance specification of this splitter. Let's go to the last one. You have a milk as the raw material, and the milk has some fat. your objective of the process is to get the fat from the milk. So you are using a centrifuge. The performance specification of this centrifuge is that the 98% of the fat which is recovered from the milk. So 98% is the system performance specification of this centrifuge. Okay, so here are three different processes. The first process is very simple. We have only one single mixer, and this mixer is the system with clear boundary, and then three input streams are introduced into the mixer, and also one output stream is going out of the mixer. Let's go to the second. Let me say this is the reactor, and reactor is taken as the system here. And 90% A plus 10% B mixture is introduced into the system, and those things, 90%, 10%, are the stream composition of specification of input stream. Also, the 60% of the reactant A is converted to the final desired product C by chemical reaction by this reactor. So the 60% conversion is the system performance or specification of this reactor. Here is a more complicated system. Includes 1, 2, 3, 4, 4 units are involved in this process, and you could take whole things as a single system, and this is the single boundary. That's it for several definition, and then it's time to go for calculation. For calculating something for processes, we need to have some equations. The required and primarily required equation is material balance equation, shortly MB. Here is the system and system boundary, and something is introduced into the system as the raw material, and something is going out of the system, that is the output stream, including desired products, sometimes byproducts, sometimes unreacted reactants. So this is the situation. And you have input or output. Input or output is the material that enters or leaves the system by crossing system boundaries. You are accustomed to the word input and output right now. And let's go into the system. There are three parameters or three terms there. And the first one is generation, and then consumption, and then accumulation. Generation or consumption is material that is generated or consumed inside the system. I'd like to emphasize this latter part, inside the system. Accumulation here is change in material inside the system. So we have three terms inside the system: generation, consumption, accumulation. In this case, stream variables are input and output, some amount of materials in input and output. Or system variables include generation of something, maybe desired products, and the side products, and consumption, maybe reactants, and accumulation, something. So those three guys are belonging to the system variables. And what is the mass balance equation? Input minus output plus generation minus consumption is equal to accumulation. This is the basic material balance equation. the dimension of each term would be sometimes moles and sometimes mass. And also, units of all terms should be the same, because this is the equation. Every term is in the same level. So again, material balance equation is read by input minus output plus generation minus consumption is equal to accumulation. Right now, you have material balance equation in our hands, which is the in minus out plus generation minus consumption is equal to accumulation. So it's time to define components used in material balance equations. It could be paraphrased into what the materials are in the material balance equations. So what kind of things should be balanced in these equations? There are three different choices. The first one is elements, or I can say atoms, like carbon, hydrogen atom, and oxygen atom. These elements could be used as the components for material balance equation for a chemical reaction of unknown stoichiometry or multiple chemical reactions. Actually, this is the most complicated situations. We don't have very small information. We don't have not very much information. Like we don't know about the stoichiometric coefficient used for the chemical reaction equation, and also we have a lot of chemical reactions. In that case, we'll use the elements or atoms as the components for the material balance equations. The second one is the most popularly used component for material balance equation. That is the compounds. For example, oxygen, water, and sugar, or something like that, which have the defined molecular formulas. They are called here compound. Let me say compound is like molecules. So you can use the compound or molecules as components used in material balance equation when you have a chemical reaction of known stoichiometry. I'd like to emphasize these two words, known stoichiometry. Only in this case, you could use the compound as component for material balance equations. The third thing is composite materials. Composite materials are mixtures of compounds or molecules of defined composition, or sometimes undefined composition like candy bars, or air, seawater, or something like that. These composite materials can be used as the component for material balance equation only if there is no change in the composition, because sometimes we don't have any information about the composition or chemical makeup of the material anywhere in the process. So you have three choices for the components for material balance equation. The first one is element, second one is compound, and the third one is composite materials. Okay, so there are several comments about the process calculation. Right now you have material balance equation. How many do you expect? I mean, how many number of material balance equation is obtained for your system? How can you expect it? So in the previous slide, I have said about the components. After you decide which kind of components are used for the material balance equation, then you can expect how many number of independent material balance equations are derived. That is to say, number of components in the stream and the system is equal to the number of independent material balance equations. Okay, so right now we know how many numbers of material balance equation is obtained from my system. And then let's go to the next thing. The next equation would be obtained from the stoichiometric or balanced chemical reaction equations. The stoichiometric coefficient can be considered as the relationship between generation and consumption, which is used to provide links between the material balance equations. Here is some examples. Some A reactant B and is going to C with the known stoichiometric coefficients. From these chemical reaction equations, you could get two independent equations. The first one, A consumption, I mean the amount of A consumed, per the amount of B consumed is equal to the stoichiometric coefficient of A per stoichiometric coefficient B with some absolute value. That is the first equation, right? And then let's go to the other one. The second one to relate the product and reactant, while the first one was relating between two different reactants. Here, moles of C generated per moles of B consumed is equal to the stoichiometric coefficient of C per stoichiometric coefficient of B. So this is the second equation. So let me think another case. How about C generation per A consumption is equal to nu C and nu A. This third equation looks different from the first and the second. However, the third equation could be obtained by combining those two equations. So the third equation is not independent of the previous two equations. So I won't count it. Here we have three stoichiometric coefficients from three entities of chemical reaction equation, and in this case we have two independent equations. So more generally I can say like that. Here is the number of n of we have n number of some reactants and products of your processes. Then you would have n-1 independent equations that related generation and consumption of different compounds. In this example, even if we have three entities or three stoichiometric coefficients, but we have only two independent equations. N is equal to 3, but we have n-1 is equal to 2, which is the number of independent equations. Okay, here is some additional equation. In addition to the material balance equations, the next thing, accumulation term. How can we have some equations about the accumulation, depending on the situation? For the steady state processes, of course, we don't have any accumulation within our system. However, for unsteady state like batch reactors, there is some values. So you should consider the accumulation term for the batch reactor or batch process. Okay, I have just copied this content from the textbook by Murphy. So the title is Process Flow Calculations in 10 Easy Steps. Even if the author is saying 10 easy steps, how can you remember the 10 steps? Anyway, let me follow those steps. Step 1, draw a flow diagram. And then step 2, define a system. And step 3, choose components or define components and define stream variables. Step 4, convert all numerical information into consistent units of mass or moles. So you should think about the units for the material balance equation. Step 5, basis. Step 6, define system variables. And 7, list all stream composition specification and also system performance specification. And step 8, set up your own material balance equations based on the component you have chosen from step 3. And then step 9, solve the problem. And step 10, check your solutions. So in the very first example, I'll try to follow those 10 steps. However, after that time, I'd like to simplify those 10 steps into 3 steps. As you know, to solve some problems, you should have the same number of unknowns and the same number of equations. So in the step A, you will decide or determine the number of material balance equations. And step B, you will decide the number of unknowns. And step C, additional equation. If you have the total number of equations, including the material balance equation from A and additional equations from C, is equal to the number of unknowns from step B, then you could solve the problem. And then step D maybe solve the problem. That's it. So I want to emphasize those 3 steps. Number of material balance equation, then number of unknown, then number of additional equations. But anyway, in the first example, I'll just follow faithfully these 10 steps suggested by Murphy. Here are additional text from Murphy's textbook, and there are detailed explanations for each step. Step 1, something like that. Step 2 here. Step 3 here. Step 4 here. Step 5 to step 10, something like that. So please read those text for your deeper understanding. However, I'd like to say all of these things in the example. Here is the very first example, 2.1. This example about the mixers, so there are no chemical reactions. And this situation is about battery acid production. In this example, I will just follow the 10 steps suggested by Murphy in the textbook. Okay, here is the text and question. Your job is to design a mixer, this is the system, to produce 200 kilogram per day of battery acid. This value could be used as a basis for your system. I mean, 200 kilogram per day is the size of your process. So, basis, and then check the unit of the basis. The mixer will operate continuously and at steady state. So, the continuous operation of the mixer. So, accumulation would be 0. The battery acid product must contain 18.68% H2SO4 in water. This is the information about the stream composition specification of the product. Raw materials available include a concentrated sulfuric acid solution at 7.78% sulfuric acid in water. This is the first reactant, and pure water. So concentrated acid plus pure water are considered as reactants, and also the other stream composition specification for the first input is 77.8% H2SO4, and the other thing is 0.8% of sulfuric acid in the pure water. So all the stream compositions are given to you. Here's the question. What is the flow rate of each raw material into the mixer? So here is the solution. I will follow 10 steps suggested by Murphy. Step 1, draw diagram. So mixer and two streams are introduced into mixer. The first one is concentrated acid and pure water. The output is battery acid stream. Then let's go to step 2. Define a system. Of course, the mixer is your system. And let's go to step 3. Choose components plus define stream variables. So we have 3 choices about the components for the material balance equation. The first one is elements. In this case, hydrogen or sulfur atom or oxygen atom. In the other case, also compounds could be used as the component for a material balance equation. So in this case, sulfuric acid and water are compounds. The other thing is mixed or the composite materials. The third choice would be composite materials like concentrated. Where is the concentrated? So concentrated sulfuric acid solution and final 18.68% sulfuric acid solution and pure water would be considered as the composite materials. Then what is your choice? Sometimes anything is okay. Sometimes you cannot use one of them. Sometimes it is better to use one of them. The composition of composite materials changes in the system, right? So the first composite material was 77.8% sulfuric acid in water. Then in the final product, these composite materials are changed into 18.68% in terms of composition. So the composite materials of the compositions of composite materials are changed. So we cannot use the composite materials as the component for this material for this process, for the calculation or for the material balance equations. So we have 2 more choices, 2 compounds like that and 3 elements like that. There are no chemical reaction in the system. And then information on composition of the acid solution is given in terms of compounds. So you could use elements and also you could use compounds as components of material balance equations. However, it is better to use compounds as components to simplify the calculations because some information is given in terms of the compounds. Okay, so let me take compounds as components. And then let's go to the next for defining stream variables. So right now you have system and 3 streams. And let me denote each stream by number, like 1 for this stream, 2 for this stream, and 3. Then the stream variables for each stream would be flow rate. The first one is flow rate, total flow rate for each stream, and the compositions of sulfuric acid and water compositions. So let me write down in this way. F1, flow rate for the stream 1. W subscript S1 means weight fraction of sulfuric acid. S stands for sulfuric acid. sulfuric acid in stream 1 with weight fraction of water in stream 1. In the same way, F2 and some more fraction of water, and F3 with weight fraction, not more fraction, weight fraction of sulfuric acid and water, something like that. So we have written all of the stream variables, okay, the stream variables. Then let's go to the step 4. Here is the step 4 and 5. It's time to check units and define basis. So anyway, let me start with the basis. So it would be basis. You should produce 200 kilogram per day of battery acid. So the basis is 200 kilogram per day, and this one is the value of F3. How about the units for each variables? You know, the unit of basis, kilogram per day, is the best choice for the unit for flow rate. So kilogram per day, and the other thing is from the text, which is the weight fraction, so weight percent. So weight percent is going to here, 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 here. Step 6. Okay, you have just defined the stream variables in step 3, maybe. Then it's time to define system variables following the stream variables in step 6. No chemical reactions, so no generation, consumption variables are required, and system is operated at steady state or continuously, so zero accumulation variable. It means we don't have any system variables in our system, so nothing inside of the box, the system. And then, okay, right now we have stream variables and no system variables. Then in step 7, I'd like to list the specification from the given information. Let me start with the first stream. The first stream, we have 77% H2SO4. So WS1 is 0.77, and of course W, or fraction of water in stream 1, is 0.23, because the sum of those two weight fractions should be 1.0 or 100%. How about the second input stream? Pure water, so 1.0. And go to the output stream. The output stream should have 18.68% sulfuric acid, so 0.186 for sulfuric acid, and of course the rest of them is going to water, 0.814. That's it. Everything is specified except of the flow rate for stream 1 and stream 2. And then it's time to set up material balance equation. How many material balance equation could be obtained from the system? You could expect the number of material balance equations is number 2, because you have two components, sulfuric acid and water. Also, let me set up the general equation of material balance equation. No generation, no consumption, no accumulation. So in minus out equal to 0. So in is equal to out. Then for sulfuric acid, we could set up this kind of material balance equations. So in for sulfuric acid is F1 by WS1, right? Plus the other in, but there are no sulfuric acid, so 0. Equal to out. Out is here, 200 by 0.186. So the final material balance equation for sulfuric acid is like that. Then you could get the value about F1 here. How about water? F1 by W1 and F2 by W2 is equal to out F3 by W3. Then you have one more equation. So two equations and two unknowns, which are F1 and F2. Then finally you can calculate the value about those unknowns here and here. That's it. We have solved the problem. And step 10, check the answer. Let me use another equation. F1 plus F2 should be F3 because this is the steady state. And so let me get the values. 48.3, 151.7 should be equal to 200. And if those values have satisfied this equation, then your answer is probably right. So that's the example 2.1, and I have just followed the 10 steps of Murphy's method. Then I'll present another methodology to solve the same problems by using my ABC step. Okay, I have get back to the process flow calculations in 10 easy steps captured from the textbook. However, I won't use the 10 steps. Instead of 10 steps, I'd like to suggest 3 steps. Step A, Step B, Step C. In the Step A, I'll try to define the number of material balance equations. How can we expect the number of material balance equations? Actually, the number of components is the number of material balance equations. So try to set up the components. And let's go to the Step B. In the Step B, I'd like to get the number of unknowns. Actually, unknowns are variables in the processes. So try to define the variables. Okay, then if the number of material balance equation is equal to the number of unknowns, then you don't need to go to Step C because we can solve the problems. Unknown equal to equation. That's it. But in most cases, or maybe almost 100%, the number of material balance equation is less than the number of unknowns. So you should use the extra equation. You should find the extra equation. So let's go to C. Additional equation you will try to find. And then A plus C in terms of number of equations is the same as the number of unknowns from B. Then you could solve the problem. And maybe you can check your solution. So I'd like to emphasize only 3 steps. A, number of material balance equation. B, number of unknowns. C, additional equation. So we are still on the example 2.1 about the mixer for battery acid production. So we have already solved this problem by using 10 steps. Then it's time to apply the step AB3 into the same problem. So step A, define the number of material balance equations. So here is the mixer and maybe 3 streams are there, and you should define the component for material balance equation because the number of components is the number of material balance equations. Then I have chosen the compound like sulfuric acid and water as components. S stands for sulfuric acid and W stands for water. Why? Because there is composition changes from concentrated acid to more dilute acid. So you cannot use the composite materials as the component for material balance equation. And second, no reaction. So we could use compounds and also elements as component for material balance equation. But if you have those two choices, it is better to use compound as the component for material balance equation. You could get some, you could pass the simplify calculation when you are using the compound instead of atoms. Number of equation, therefore we have two components for this process, S and W. So two components. It means number of material balance equation is number 2. Okay, let's go to step B. Define number of unknowns. Then before going to define unknowns or variables, let me think about the units of those variables. So practically the hints for the units are coming from basis. 200 kilogram day of battery acid you should produce. So it is the basis or scale of parameter. So I'd like to take kilogram per day for the unit for flow rate. And how about the number of unknowns? There are no reaction, so generation and consumption equal to 0, and steady state accumulation is 0. So no system variables in this system. So we can focus on the stream variables. So for the streams, usually flow rates are defined and also their compositions are defined. So 3 flow rate, F1, F2, F3 for stream 1, stream 2, stream 3 respectively, and also compositions, 2 compositions, sulfuric acid, water, and only water for the F2 or stream 2, and water and sulfuric acid and water compositions for stream 3. So we have defined the all stream variables, and let me count those variables. No system variables plus 3 flow rates and 1, 2, 3, 4, 5 compositions. So totally 8 variables. That is to say 8 unknowns are there in our process. So unknown, number of unknowns is 8. So it means we need to have 6 equations more, because at this time we have only 2 equations. So let's try to find more equations or values in step 3. So from the stream information you could define like sulfuric acid weight fraction in stream 1 is like that, and 3 like that, and WS1 plus W1 is equal to 100%, the other 100%, and also for the second stream of input is pure water, so the weight fraction should be 100%, plus basis. Basis is one of the equation or fixed values. So let me count those number. 1, 2, 3, 4, 5, 6. So 6 equations, additional equations are obtained. And also you have already had the material balance equation. Of course, in this step you should set up the equations. And in is equal to out for sulfuric acid, and in is equal to out for the water. So 2 equations. Then you can solve the problem, and also you can check the answers. That's it. So I have used 3 steps ABC for solving the same problems. Here is the second example about the ammonia synthesis. So we are treating a reactor in this example. A gas mixture of hydrogen and nitrogen, 2 reactants, is fed to a reactor. So this reactor is the system where they react to form ammonia. So ammonia process. The product is ammonia. The nitrogen flow rate into the reactor is 150 gram mole per hour. So this one or this value can be considered as the basis, and also you can get some hint from the unit of the basis. And the hydrogen is fed at a ratio of 4 gram more hydrogen per gram more nitrogen. Another equation or some information. The balanced chemical reaction is like that. Okay, so we have the balanced chemical reaction equation. It means it is the best to use the compound as the component. Like what is the compound here? Nitrogen, hydrogen, and ammonia. 3 compounds. Of the nitrogen fed to the reactor, 70% is consumed by reaction. So the 70% conversion is the system performance, the specification. The reactor operates at steady state. It means accumulation is 0. What is the flow? Oh, here is the question. What is the flow rate? The gram mole H, the same unit. So it would be better to use this unit for material balance equation of nitrogen, hydrogen, and ammonia in the reactor outlet. So that's it. Step 8. Define number of material balance equation. For defining them, we should define the element. So I have said it is better to use the compounds as the component because we have already had the balanced chemical reaction equation. So we have 3 compounds: hydrogen, the same thing, nitrogen, the same thing, and ammonia. So we have 3 components which are compounds. So number of material balance equation will be 3. And let's go to step B. Define number of unknowns. Unknowns means variables. So let me start with the system variables. We have the reaction, so we should consider the system variables, not like in the mixer. So how about generation? Okay, so nitrogen, hydrogen, the ammonia. N stands for nitrogen, H stands for hydrogen, A stands for ammonia. So N generation, no N generation, no generation term for reactant, so no generation for N and H. Instead of generation, we would have consumption term for nitrogen and hydrogen, so we have 2. How about ammonia? Ammonia is product, so there are no consumption term for ammonia, only generation term is available for ammonia. We have 3 system variables, and then let's go to the stream. Let me denote this one as stream 1 and this one is stream 2, and hydrogen and nitrogen are introduced into the reactor, so H1 and N1. The other thing, H2 and 2, H2, ammonia. So we have 1, 2, 3, and 6 and 8. 8 unknowns are there in our processes. We need to have 5 more additional equations or constraints. Let's go to step C. Step C. So in this step, you will try to find 5 more additional equations. But before going to find them, let me set up the material balance equations. We have 3 different components. They are hydrogen, nitrogen, and ammonia. So let me set up the material balance equation. Here is the nitrogen balance equation, and input minus output plus no generation minus consumption is equal to no accumulation. In the same way, input minus output minus consumption is equal to 0. How about the ammonia, the product? So no input minus output plus generation minus no consumption is equal to 0 because your process is working on the steady state condition. So 3 equations are here, and then let me try to find additional equations. you could get two additional equations from chemical reaction equation, because you have three entities in these chemical reaction equations. It means you have three different stoichiometric coefficient. Then you could get two more information. For example, H consumption from here to N consumption from here, then stoichiometric coefficient of H2 here and 1 here, so 3. So those two consumptions are correlated to each other by 3. And also, how about ammonia and nitrogen? So ammonia, nitrogen, 2 over 1 is equal to 2. So two equations from chemical reaction equations. We have discussed about that in the previous slides. And then three unknowns are remaining, or three unknown not defined equations are remaining. So basis, of course, this is the good constraint. And then from the text of the questions or problems, hydrogen is fed at a ratio of 4 gram more hydrogen gas per gram more of nitrogen gas. So H1 is equal to 4 times of nitrogen 1. Then the value of N1 is here, so 600. The other thing is the system performance specification, 70% conversion. So the consumption amount of nitrogen is 0.7 of the input, then 105. So 3 more equations or constraints from given information. Then you have 8 unknowns and 8 equations. Then you could solve this problem. Example 2.3, separators, about fruit juice concentration. Until now, you have had the example about the mixer in the first example, and then reactors in the second example. Then it is time to go to separators, the third example. Fruit juice is a complex mixture of water plus fructose, pulp, citric acid, and other acid, acetate, and other chemicals. It is very complicated and we cannot define the exact compositions. Fresh fruit juice from the fruity fresh farm contains 88% water. It's a kind of composition. So water composition is 88%, and the other components or the other materials are included in the fresh juice, fruit juice, is 12%. So we could split one fresh fruit juice into 88% water plus 12% of other material. A fruit juice processor buys a batch of 2680 pound fresh juice from the farm, and then this processor makes concentrated juice by filling an evaporator with the fresh juice, evaporating 75% of the water, and then removing the concentrated juice. So the process is the evaporation, or this is a kind of separator. Then the objective of this evaporation is to concentrate the fruit juice. The question is, how much water in pound must the evaporator remove? If the processor pays 0.09 per pound for the fresh juice and sells the concentrated juice for 0.5 per pound, can he make a profit? Okay, there's the questions. And start with step A. Define number of material balance equation. It means we should choose the component for material balance equation. So here's the evaporator and some fresh juice, and then evaporated water plus concentrated juice. That is the process of you are studying. And it is better to the fresh juice. I mean, it is better to split the fresh juice into solid part and water part, because we know the composition of water. Actually, S stands for solid and W stands for water, and S is the composite materials, including fructose, pulp, citric acid, blah 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 blah. So we cannot exactly define the solid materials. However, we know the composition of these solid materials, and also the composition of water. So I'd like to use S and W, solid and water, as components for material balance equations. It means number of material equation is equal to 2. Let's go the step B to define number of unknowns. Unknowns are variables, so it's time to define the variables. Evaporator and the fruit juice, which is a mixture of solid and water, is introduced into the evaporator. And finally, we have the fruit juice with more concentrated solid, so as this one. And then in the second stream of output, we could have some water, which is evaporated from the raw materials. So S1 W1, W2 S3 W3, stream 1, stream 2, stream 3. So 5 unknowns or 5 variables are defined. We don't have any reactions, so there are no system variables. Okay, let me think about the dimension of each variables. Batch reactor. This is the batch reactor. Pour everything into the evaporator, and during evaporation something is going out, so water is going out. And then after the evaporation, then we'll get the S3 and W3. So batch reactor. And flow rates are not required. Actually, mass or moles are required for describing the variables. So mass. Okay, so mass, and also no reaction. So moles is not required. If you have some reactions, moles rather than the mass is better as the unit of the material balance equation. However, here is no reaction, so mass or moles, anything is okay. And also the basis is given in pound, so it is better to use pound as unit for these material balance equations. Step C. So right now we have 5 unknowns and 2 mass balance equations, so we should find 3 more additional information or equations. Before going to have more information, let me set up the material balance equations. So we should have 2 different material balance equations, one for the water, one for the solid. So 1 input and 2 output. W1 is equal to W2 plus W3, and S1 is equal to S3. That's it. And the other thing, basis 2680 pound fruit juice is introduced into the evaporator, so S1 plus W1 is equal to 2680 pound. And the fresh juice in the input is 88% water. Water. So W1 is equal to 0.88, 88% of water, right? So these values of water containing in the stream 1. How about W2? The evaporator removes 75% of water in the fresh juice. The water in the fresh juice is W1, and then 75% of W1 is going to W2. Which are evaporated from the evaporator. Then you can fix this value. Then finally you can obtain the all values of stream variables. That's it. And then let me say about the profit. Right now we have all values. water amount, solid amount, water, solid amount. Then it's time to calculate the profit. So the total amount of concentrated juice is 910 pound, right? 910 pound concentrated juice, and each pound of concentrated juice the processor earn money at $0.5. Okay, and but here's the cost for getting the fresh juice from the farm. So 2680 pound fresh juice comes from the farm, and then each pound the cost is like that. So the processor will earn money at $215. That's the example 2.3.